Okay, let us start. So, I will be talking on one particular aspect in econometrics or financial econometrics in particular. That is very important one. That is why I have selected that topic. So, before that, let us have some overview on econometrics. We have a distinction of econometrics based on data and economic fields. Based on data, we have three types. That is cross-section econometrics, time series econometrics, and panel econometrics. So I believe that all of you are familiar with these data sets, cross-section, time series, and panel. The last two are very much important in the context of financial econometrics. Time series, especially time series data sets. Occasionally, or in some cases, we also use panel data in financial econometrics, mostly time series. So we have some separate sessions on time series econometrics. Otherwise, today we will be dealing with the general econometrics. Now, based on economic fields also, we have two types, microeconometrics and macroeconometrics. Microeconometrics usually is characterized by the analysis of cross-section and panel data. And usually it focuses on individual consumers, firms, and micro-level decision makers, other micro-level decision makers. Now, in this particular case, we have a number of theoretical tools taken from microeconomics, including utility maximization, profit maximization, market equilibrium, and so on. And these we also apply in financial economics, and hence we have the significance of financial econometrics also in microeconometrics. Then coming to macroeconometrics, here the analysis is on time series and panel data. And as the name of macro suggests, the variables that we consider here are aggregates such as price levels, money supply, exchange rates, national output or national income, investment, economic growth, and so on. A large number of macro variables. And usually time series is associated with the macroeconometrics, and hence financial econometrics also is usually with the macroeconometrics. But we also use in financial econometrics panel data. Now, actually the boundaries between microeconometrics and macroeconometrics in financial econometrics are not very sharp. We know that financial econometrics deals with the long time series data and sometimes, as I told you earlier, with the panel data also. But usually there is a sharp focus on models of individual behavior. So that means in econometrics, to that respect, that is, as long as we give a focus on the individual behavior, then we have microeconometrics in financial econometrics. At the same time, we know the analysis of market returns and exchange rate behavior cannot be exclusively macro or microeconometric. So, as far as financial econometrics is concerned, we can have both micro and macroeconometrics. That is, we study long-term series data on individual firms, that is the micro aspects, or individual agents, financial agents. And at the same time, we also deal with the broad financial aspects as if in macroeconomics. Now, these are some of the books directly dealing with financial econometrics. The Chris Brooks book is very famous for an introductory econometrics for finance. Now it is in its fourth edition. And I think this some earlier work, even the fourth edition copy of Chris Brooks is available in the Google. So you can try that. Then there is another book by Campbell, Law and Macmillan. This also is a very famous textbook on the econometrics of financial markets. Then by Peiji Wang, a book by financial econometrics, then it is not as famous as the next one by Zhe, Ruiz Zhe, says Analysis of Financial Densities. Another one is Financial Econometrics from Basics to Advanced Modeling Techniques. This is written by a number of econometricians. It's a very good book. Very simple one compared with, of course, simple. The Chris Brooks book also is very simple. Then we have an edited book by High Frequency Financial Econometrics, Recent Developments. So, of course, a large number of other books are also available, but I'm just showing a few. Now, this financial econometrics is considered the science of modeling and forecasting financial data, such as asset prices, asset returns, interest rates, financial ratios, defaults, and recovery rates on debt obligations, and risk exposure, to say a few. And this is also called the econometrics of financial markets. Econometrics of financial markets. There are three fundamental enabling factors that make the development of financial econometrics possible. The three are the availability of data at any desired frequency, including at the transaction level. We know that today we are in the position of very high frequency data, including not only just the hourly data. Earlier, of course, we had daily data, but now not only the hourly data, we are getting the every moment we are getting a particular data set for every moment. So that's the availability of that high frequency data was the first enabling factor for financial economics. Then availability of powerful desktop computers at an affordable cost, and the availability of off-the-shelf econometric software. A large number of econometric software are available these days, including Stata, eViews. Then, of course, we have the free software such as R, Python, then Gretl also. So I will be introducing Gretl in the afternoon session today, and we will continue with that Gretl. Some of you may be knowing about Gretl. Anyway, it's a free software, and the beauty about Gretl is that it is menu driven, unlike the R. So we just give click and we get the result. Click, we get the results. So that's the beauty of Gretl. So actually the combination of these three factors push advanced econometrics within the reach of most of the financial firms. such as banks and asset management fields. That's why today we have the particular field, financial econometrics. So as I have already told you, financial econometrics is applied to either time series data such as the returns of a stock or cross-sectional data such as the market capitalization of all stocks in a given universe at a particular time. With the progressive diffusion of high-frequency financial data and ultra-high-frequency financial data, financial econometrics can now be applied to larger databases, making statistical analysis more accurate, as well as providing the opportunity to investigate a wider range of issues regarding financial markets and investment strategies. Now, there are three key steps in applying financial econometrics at work. These three steps are there for general econometrics also. So the three are, first we have model selection, then we have model estimation, then we have model testing. So here I will be concentrating on the last one, that is the model testing, and assume that you are already familiar with some of this model selection and model estimation. Let's start with the step one in model selection. We select a family of models with a given statistical properties, and of course we know these models entail mathematical analysis to justify our particular choice. What we do here is that we use, for example, an econometric tool such as a regression analysis to forecast, say, stock returns based on some fundamental corporate financial data and macroeconomic variables. Then we have the second step, model estimation. In general, the models are embodied in mathematical expressions that include a number of parameters that have to be estimated from sample data. I believe that you are all familiar with the statistics, especially the distinction between a population and a sample, and the difference between parameters and statistics, and then estimation procedure, and so on. If you have any doubt, you can ask me then and there. Okay. If you are not familiar with the parameters and statistics, then you can ask me. I shall explain those things. Now, in this particular case, suppose that we have decided to model returns on a major stock market index, such as the S&P 500, with a regression model. And in this particular case, we have to estimate the corresponding regression coefficients based on historical data. And coming to the estimation, we have two main aspects. That is, finding the estimates and then understanding the behavior of those estimates. For example, the market capitalization of firms is easily observed. Of course, there are computations involved in finding the market capitalization. That is, we get market capitalization by multiplying the value of a stock by the number of outstanding stocks. But the process of computing that market capitalization is essentially a process of direct observation. But that is not the case with some other cases. That is, when we come to the estimation, we are not able to directly observe the parameters that appear in the model. For example, consider a very simple model of trying to estimate a linear relationship between the weekly return on General Electric stock and the return on the S&P 500. In terms of the simple linear regression analysis, we can write this particular relationship as the following. That is, return on GE stock, General Electric stock, is equal to alpha plus beta of return on S&P 500 plus an error T. This, we have two parameters in this particular simple linear regression, that is alpha and beta, and they are referred to as regression coefficients. And in this particular case, the dependent variable, that is the return on GE stock, and the independent variable, return on S&P 500, are directly observable. But the two parameters alpha and beta and the error tree, they are not directly observed. We have to estimate them using the historical data. So there comes the importance of estimation. Now we come to the last step of model testing. Now, usually, once we have estimated a particular model statistically, that is econometrically, what we do is we go for the hypothesis testing on the coefficients of a model. That is the model significance or hypothesis testing. But actually, and then we have estimated a particular model econometrically. We go for the model significance testing, that is the hypothesis testing on our estimated coefficients based on, of course, our null hypothesis for the parameters of the model. And there everything stores. And then we report the results. That's all. Actually, that is not the correct procedure. The model testing also includes something else also. And that is more important than this so-called first step of model significance testing. That is, we need to see whether the assumptions that we have used in the case of the estimation are met or not. So actually, in respect of only one method in time series econometrics, that is in ARIMA modeling, this particular case is still followed. But unfortunately, in most other cases, whether it is in cross-section data or time series or panel data, the investigators usually do not care for this particular aspect. But this is very, very important one, because the estimation is possible under certain conditions. And whether the estimates are valid or not depends on meeting these assumptions. So we have to see whether these assumptions are met or not. I am now going to explain this particular model testing. That is the what usually called model adequacy test. Model adequacy in econometrics or financial econometrics. So before going for the hypothesis testing on the estimated regression equation, we have to see whether our model is adequate or not. If the model is not adequate, then it is useless. We cannot use that. That means we need not go for the significance of the estimated model. So first we have to see whether our model is adequate or not. And this is the case that I am discussing today. And this is very, very important, because these days, unfortunately, people just ignore this particular aspect. So we have to take the results, thus reported results, with a pinch of salt. It's doubtful whether the estimates are really valid. It's doubtful. Unless the model adequacy tests are reported, the the estimation procedure and the results are under cloud. So we cannot take them without doubt. Now I shall start with a multiple regression analysis. Suppose we have n observations on the dependent variable y, and we have k minus 1 variables and k parameters. That means y is a function of k minus 1 independent variables and a random error t. And when we write it as a linear regression, we have this equation. yi is given as beta 1 plus beta 2 xi2 plus beta 3 xi3 and so on, beta k xik plus ui. Here, remember, we have k parameters, beta 1, beta 2, beta 3 and so on. Beta k are the parameters, and these parameters we have to estimate using the sample information. We have no variable with beta 1 because beta 1 is the so-called intercept constant in the linear regression. The coefficients are beta 2, beta 3 and beta k associated with the independent variables. We have k minus 1 independent variables, and remember k parameters. And if we write in detail this particular expression on yi, where I is from 1 to n, then we have this particular these equations. For the first observation or the first unit, maybe the first frame, first factory, then we have y1, then y2, y3, and so on yn. Remember, in all these cases, the parameters remain constant. We have the same intercept and the same coefficient for x2, same coefficient for x3, and so on. And it is these parameters that we have to estimate using the sample data. So for estimating these parameters with the sample data on y and x in general, we usually use the ordinary least squares. OLS is the very simple method. These days, of course, all methods are simple given the powerful computers, but traditionally we have used the ordinary least squares method for the linear multiple regression. Now, for a particular case, suppose we have a symbol that is bivariate. That is, we have only two variables, one independent and a dependent variable. And like this, yi equals alpha plus beta xi plus ui. Now, this is given as the population relationship between the two variables yi and xi. And based on this particular model, I told you earlier that we have the mathematical models, and these mathematical models capture the population relationship among the variables of our interest, and using the sample data, we are estimating that particular population relationship. And suppose we have estimated a regression using the sample data like yi hat equals alpha hat plus beta hat xi. Now remember, whenever we put a hat on a particular variable, for example yi, we are putting a hat on this yi. This becomes the estimated value or the computed value of this yi. So yi hat is an estimate or estimator of yi. Then alpha hat is an estimate of alpha, the parameter. So alpha hat is the sample estimate. Beta hat is the sample estimate of this beta. And then we have the sample data xi. So this gives us the estimated regression equation, sample regression equation. And given these values, now we can find out an estimate of this error tree ui. using this yi and yi hat. That is, if we subtract yi hat, if we subtract yi hat from yi, we get an estimate of this ui. That is given here, ui hat equals yi minus yi hat. And yi hat is our alpha hat plus beta hat, xi. This ui hat is an estimate of the error term and it is obtained as a residual from yi. This is a residual. Yi minus yi hat is a residual. Therefore, this estimated error term is usually called residual. So these are the residuals. So remember, we have these estimates. Now remember, as I told you earlier, these estimates are obtained from the directly observable sample values of xi and yi, whereas this population values variables or values are not directly observable. That is, we do not know anything about alpha, we do not know anything about beta. Same is the case with this error term. But using the sample data, we can estimate them. Now, we come to a very famous theorem, which is called the Gauss-Markov theorem. The theorem says that out of all the class of linear unbiased estimators, the OLS estimators have the smallest variance. That is, they are more efficient. The OLS estimators are more efficient, or they are the best. The best means they have the minimum variance among all the linear unbiased estimators. That is, in general, the least squares estimators are said to be blue. Blue means B for best, L linear, U unbiased, E estimators. Best linear unbiased estimators. And OLS estimators are best in the sense that they are the more efficient or the most efficient. That is, they are the best estimator. Then they are the linear estimates, they are unbiased estimators are also. And all these, the blue properties are subject to certain assumptions. These assumptions are called Gauss-Markov assumptions. So the OLS, ordinary least squares, are based on certain assumptions. Only if these assumptions are satisfied, then the then only the least squares estimates are blue. Now, all these assumptions we can write as an acronym, no line. That is the assumption of non-stochastic independent variables. Then orthogonal x, and that is the independent variable and the error term. Linearity. Then independence of areas. We will come to all these assumptions in detail. Then we have the normality of error, then equal variance, which is also called Homoscedasticity. So in general, we have the assumptions of the OLS in terms of assumptions on U and the assumptions on the independent variables. So we can, all the assumptions we can divide into these two cases. Assumptions on the error term and the assumptions on the independent variable. Now these are the assumptions for the error term U. That is, they have zero mean. On an average, the error term is zero. Then the disturbances are normally distributed. Normality assumption. Disturbance is the error term. The error term is normally distributed. Then the variance parameters in the covariance variance matrix of this error term U are the same. That means this error term U has a constant variance, and that constant variance is called homoscedasticity. We know homo means the same or constant, and scedasticity is the Greek term for variance. So instead of variance, sometimes we say scedasticity. So if we have a variance function, then we also say that we have a scedasticity function. So homoscedasticity means constant variance. So that simply means that there is no heteroscedasticity. Hetero means different. Scedasticity variance. The variances are not constant. So with every independent variable for the error term, there is a different variance. That is the assumption of heteroscedasticity. The next assumption is the no autocorrelation assumption. That is, the error terms are not serially correlated. So there is no autocorrelation as such. We will study about this autocorrelation when we come to the time series econometrics. And this particular assumption also is called independence of error. That is, the error terms are independent of each other. Now see, this U includes U1, U2, U3, U4 and so on. So this U1 is independent of U2, U1 is independent of U3, U1 is independent of U4 and so on. Similarly, U2 is independent of U3, U2 is independent of U4 and so on. That is, these U variables are not correlated. That is independence. They are not correlated. That means they have no serial or autocorrelation. If these three assumptions are satisfied, then our error term, this U, is called a spherical error. So we have by a spherical error, we mean that the error term satisfies these these three assumptions except the second one. It need not be normally distributed one. Okay, if it is normally distributed, then we have a normally distributed spherical error or Gaussian spherical error, because the normal distribution also is called a Gaussian distribution. So if this normality assumption also is satisfied, then we have a Gaussian spherical error. Otherwise, with zero mean, homoscedasticity and no autocorrelation, we have a spherical error. Now we have some assumptions for the independent variable set. The entire independent variable set X is assumed to be non-stochastic. That is, they are not like the error term U. We assume that they are like fixed values from sample to sample. Of course, we can relax this particular assumption and think of stochastic X also. That is a separate subject in econometrics. Now, we have a very important assumption in the framework of multiple regression, that there is no perfect multicollinearity. That is, there is no perfect linear dependence between two or more explanatory variables. This is very important because if there is any perfect multicollinearity, then we will not be able to estimate that particular equation. So that is the case of no perfect multicollinearity. Remember, all these assumptions we will consider again when we come to the model adequacy. The next one is the orthogonal X and the error term. That is, the explanatory variable and the error term are independent of each other. That is, the explanatory variables and the error term are not correlated. Their covariance is zero or their correlation is zero. That is why it is called orthogonal. Orthogonal simply means independence. So independent X and error term. Then finally, we have another assumption that there should not be any specification error. Usually, the specification error happens by way of excluding some relevant variables or including some irrelevant variables or incorrectly specifying the functional form or committing some measurement error. We will come to all these assumptions later. So these are the wireless assumptions, and only if these assumptions satisfied, the wireless estimate is become blue, that is best linear unbiased estimate is. Now, how do we find whether these assumptions are satisfied or not? So we are coming to what is called the model adequacy test. And this model adequacy test we carry out on the residuals that we get from our regression. You know the residuals we are getting from subtracting the estimated value from the original value. So we analyze this residual to find whether our model is adequate or not. So as I have already told you, the residuals are the estimate of the error tape UI, that is UI hat, obtained as a residual, that is yi minus yi hat. So we have to check the assumptions of regression by examining these residuals. And this usually we do using the graphical analysis of residuals. And in addition to the graphical analysis of residuals, we have, of course, certain statistical tests for each of the assumptions. So we will consider both the graphical analysis of residuals and these tests on the assumptions. So we are coming to the model adequacy diagnosis. And as I have already told you, this is an important stage before hypothesis testing in forecast modeling. And in 2001, I had a serious working paper. It is available in the net or it is available in my ResearchGate page. So I believe you are all familiar with the ResearchGate. You can go to the ResearchGate and find out my page. And all my lecture series are available there, all my publications. And this working paper also is available there. It is important that you read this one. This is electricity demand analysis and forecasting. The tradition is questioned. That is, I was questioning the tradition of not reporting the model adequacy diagnosis. So it is good that you read this particular working paper. Now, what is this model adequacy? Now, the estimated model we say as adequate if it explains the dataset adequately. That is, if the estimated model contains or captures all the information in the dataset, then that model, that estimated model is said to be an adequate model. So telling this is equivalent to telling that if the residual, that is the residual we are getting from subtracting the fitted model from the actual one, actual information. So that residual does not contain or does not conceal any explainable non-randomness left from the explained model, then our model is adequate. Now, what is this explainable non-randomness? We know non-randomness or explainable non-randomness refers to some patterns, and patterns represent information. So if the residual actually has some information, some explainable information, then that particular model is not adequate. So the residual should be purely random, or what is called a white noise in time series analysis, or in general a spherical error in econometrics. We have already seen the error term U is said to be a spherical error. Similarly, the residual that we get as the estimate of that error term must be purely random, or it must be a spherical one. It must be a spherical one. It should not contain any information at all, so that the estimated model contains every information possible from the dataset. In that case, we can say that all the OLS assumptions are satisfied for this model, and the model becomes adequate. That means it is the OLS assumptions that we have to consider to see whether they are satisfied or not. So once we have estimated an OLS model, remember OLS model, ordinary least squares model, then we have to see that all the OLS assumptions are satisfied. Only then our model is adequate. Only if our model is adequate, we can go for hypothesis testing, and after that for the forecasting. If the model is not adequate, then it is a useless model. We cannot use that. Now, this is the residual analysis for linearity. So, what we do is we get the residuals, and the residuals we plot against the independent variable x. And if they have some nonlinear pattern, then that means they are not linear. But here we find that the residuals are linear. In this case or this case, they are linear. Then whether they are independent or not, the error independence, that is no autocorrelation. So if the residuals have a pattern like this, or a pattern like this, a cyclical pattern, then they are not independent. That means there is some autocorrelation in the residuals, some autocorrelation in the residuals, so that the no autocorrelation assumption of the error term is violated. Now, in this particular case, we don't find any autocorrelation. There is no pattern. Therefore, here the residuals are independent of each other. There is no autocorrelation. Our assumption is satisfied. Then the normality assumption, whether the arrays are normally distributed or not. In this particular case, the residuals are not normally and independently distributed with the zero mean and sigma static deviation, because the skewness and kurtosis assumptions are not satisfied. The skewness value is 5.1718. It is very high. Actually, for normally distributed error, the skewness measure must be 0 or around 0 or statistically 0. And the kurtosis must be close to 3, or it must be 3. Here the kurtosis measure also is very high. So we have the p-values given in the test. The p-values are all much less than 5% or 0, close to 0. Therefore, we reject the null hypothesis of no skewness and no kurtosis. That means the arrays are not, or the residuals are not normally distributed. And the histogram of the residuals also show that they are not normal. Now, what are the implications of non-normally distributed errors? Now, if the residuals are not following the normality assumption, then the estimates of alpha and beta are also not normally distributed. But remember, the estimates that we get from OLS are still blue, because this particular assumption is not essential for estimation. The normality assumption is not essential for estimation. We are not using this assumption for estimating the OLS estimates. So the estimates are not affected by non-normality. They are still blue. That is, they are unbiased and they have minimum variance. And they are the best one. Now the problem with the non-normally residuals is that we are not able to do our hypothesis tests. So it is only the hypothesis tests which are affected by the violation of this assumption. That is, alpha and beta are normally distributed only if the residuals are normally distributed. And we can have parametric tests based on sampling distributions. That is the t-test or the z-test or chi-square test or f-test. We can have only if the estimates are normally distributed. If they are not normally distributed, then we are not able to do the parametric tests. That is the problem. So the non-normality problem affects our hypothesis tests, parametric hypothesis tests. Now, what are the causes for non-normally distributed errors? This is generally caused by a specification error. For example, by omitting an important variable. It can also result from outliers in data and having a wrong functional form. So it is essential that once we have obtained our data, we have to see whether there are any outliers in our data. Because if outliers are there in our data, then that will also affect our estimates. We know the mean is partly affected if outliers are there. So regression coefficients are also affected by outliers. So we have to check out for the outliers in data. For example, by using box diagram, the box and this case diagram. So those will give us some idea whether there are any outliers or not. If there are outliers, then it is safe that we omit them. Then by using some wrong functional form, we can generate non-normally distributed residuals. That is using a linear format, whereas the original one is the log linear one or the logarithmic one. So using a